go over a really interesting sort of circuit example, sort of resistive capacitive circuits. And I'm going to use this, kind of keep it simple in terms of op-amp types of structures, but just so you kind of see what is possible with some very interesting circuit topologies. Now, so the circuit I'm looking at is the one below me. And you might say, it's an interesting circuit. I see a cap here, some R and C around an op-amp, and I have this voltage controlled current source, and you think, this is a lot of stuff. What do I make sense of it? And you might ask, well, where do I begin with this, right? And so I want to try to think through part of the intuition and try to explain a couple key parts of this. So you might look at this op-amp circuit and you go, okay, well, what do I know about this? Well, I probably know that this is going to be an integrator structure because I'm going to be seeing an R here and a C here. So this R basically gives me a current going in, and that current gets sort of put onto the capacitor. So if I were to look at this just from simple sort of feedback, I'm going to expect to get something which is going to have sort of 1 over S and SC and then R. So if I have RC as my time constant, I'm going to get a 1 over minus S tau V out of S. And you're like, okay, that's kind of interesting. From this output node to this V1 node. Now that might seem a little bit strange why I'm using that particular point, but at least I know that that does something. Now the other thing I have to pay attention to is that if I looked into this node, looking into this resistor, it looks like I just have a resistor to ground. Why? Well, again, with this op-amp, I know these terminals have got to be close to each other, assuming the output voltage stays in the power supply. So I know these two voltages have to be nearly equal, which that means that this is a voltage with a resistor between it to ground. So it basically just looks like a resistance to ground. The input resistance is just R. And you're like, oh, okay, that gives me something else I can now work with. And you think, well, I can take all of this and then I could sort of substitute because I have this expression of V1 to V out. Here's V1. Here's V1. The only place I use it is in this voltage controlled current source. And at first you're looking at this topology and you think this is really a weird kind of feedback, but it's something we can start to use. And you think, well, okay, let me substitute all that in. And what I notice in Laplace domain is I've got something of 1 over S tau R times V out. And I step back and I think, hold on. Something with a resistance that is proportional to S is something we call an inductor typically. But somehow I don't have any inductors in this circuit. I just have op-amps, resistors, capacitors. So what happened? Well, this interesting topology of having an integrator going into a current source, this kind of loop, is called a gyrator. And is a very interesting circuit that basically says, let me take a state holding element, in this case this capacitor, and effectively invert its sort of state variable part of the impedance. So where resistance for a capacitor is 1 over SC, and now becomes a resistance that's proportional to S. This turns out to be a very valuable function because in so many places inductors, for example, are very hard to find or very hard to get in a quality that you'd want to use. So sometimes we'll kind of build sort of second order structures in this way. And the net effect is I've got something that looks like an inductor where the inductance looks like R squared C. So I could just think of this element as an inductor, call it an inductor L. And if I were to solve for this, I would get just a transfer function of S squared LC, of LC S squared plus 1, plus the term in the middle is going to be that inductance over 2R. Why 2? Well, it's partially because this resistance is actually cut in half. Why? Because I have an R and an R in parallel. So the net effect is that 2 R's in parallel gives me a resistance that's half that amount. And that's actually where this is coming from. And I could take this structure and go, okay, now I can look at what is my tau and my Q of this particular structure, and L and R. And you think that's great, except one interesting piece happens. You're like, but wait, I know more than that. I know what the L is. I know it's R squared C. So if I start substituting that back in for where I get the L's here, because that is what it is, that's where the L actually is, I actually get this trend, and I keep tau as RC like I did before. My transfer function is s squared tau squared over 1 plus s times 2 times tau squared. And you think, oh, that simplified nicely. In fact, further, it turns out because this is 2, my q is a half. And we know that q at a half is also a very critical point. Because for q, less than a half, I get two different real roots. And for q greater than a half, or q greater than a half, I get 2 complex roots. So q is at a half, which means I get 2 identical roots.